So it is already 2 minutes past the 12 o'clock. So should we start now? Today we will have an event for as our he's not a guest as our speaker. Ivan is a PhD candidate in computer science at the King Abdullah University of Science and Technology. He is a member of Professor Peter Richard's group.
Yeah.
His research interests mainly lie on deep learning, model compression, federated learning, with a particular focus on quantization and pruning for efficient development and deployment and inference for large language models. Before joining KAUST, Ivan got experience as an undergrad researcher at the Bunker Institute of Nuclear Physics in, how to pronounce that? Novosibirsk in Russia.
Yeah.
Followed as a role of a deep learning junior researcher at Expasoft as a researcher assistant at the Lavatiev Institute of Hydrodynamics. And today he will talk about his work at Thanos. And let's get started.
Thank you very much for the introduction. Today my talk will be about large language models, which means that because this topic is very hot, probably you will be listening a little bit more carefully. Specifically, this work was done during my MS thesis here at KAUST. Now I'm at the beginning of my PhD, so I think I'm very glad to stand here in front of the computer science audience, because probably I will be collaborating with some of you. The plan for today is the following. I will tell you about large language models, how they work, of course, in not large details. Then I will tell you about how to make large language models a bit faster by applying pruning. Then I will present you my work, Thanos pruning, and of course tell you about some implementation details and results. Let's start with large language models. What it is for and how does it work? So I think all of you knows that large language model is kind of a mapping of the input words, for example, write a story, into some output. For example, once upon a time and so on. But this is a very complicated problem. We split it on a more simple one. We don't have a bunch of text. We give it the bunch of input words, write as story. This is a separate words. And we want to have the output in a bunch of the output sequence words, once upon a time. But it's complicated to work with words. That's why we have some high-dimensional representation of every word, because words have different length. It's difficult to work with them. But if you have some process that allows you to obtain high-dimensional representation of the word, that gives you some information, that might be much, much more easy to work with such representations. So that's why we have these high-dimensional vectors instead of words. And also, we give a sequence to every word. 1, 2, 3, to present the order of words in your sentence. And we split this problem in even more simplistic, because we don't want to generate the full story at a time. What we really want, we want to generate the new token, the new word in the sequence, the next one. And that's exactly how we talk. We actually, when we speak, we think about the few next words in the sequence. We are not trying to write a full story at a time. But large language models do not work with words. It is working with probability distribution, meaning that you have the vocabulary of all possible words that can be generated by this large language model. And then for every single word in this vocabulary, you have the probability of this word to be the next one in the sequence. For example, here we can see that the probability of the word once is very high, because many stories starts with once upon a time. So we know that the probability of this word should be high. But not many stories starts with hello, and that's why the probability of the word hello is not too high. And there are no stories that start with have. That's why the probability for this word is 0. And what we actually do, we just take the word with the highest probability. And when large language model is just the mapping of the input words, the input sequence, into one word, the next sequence. If you want to generate the next one in a sequence, you just give this from the previous generation step into your input sequence, have this large high-dimensional representation of the word, and then you have the next generation step where you have the next tokens and the next probability distribution for the next word. You see that the highest probability should be for the word upon, because once upon a time, and so on. That's actually how large language models work. And of course, the most complicated and the most interesting part of this pipeline is these large language models. Let's focus our attention on how it is constructed. Every single large language models consist of a bunch of identical blocks that are stuck in front of each other. So we have absolutely identical blocks, but with different weights inside. Let's consider one of these blocks. We have the input x. As we mentioned before, we don't have words, we have high-dimensional representation of these words. And what we do, we actually construct a tensor because we have several words. For each word, we have high-dimensional vector, one-dimensional. Then we have several words. That's why we have the input matrix. If you have several input sequences, that means that the batch size is larger than 1, and that x will be a tensor. But let's now consider only one input sequence. So you have a matrix where every single row represents some word in your input. And then what you do with this input, you simply apply some matrices. They are called queries, keys, and values. These three matrices. But you just simply multiply these three green, yellow, and blue matrices on the input x. And then you have done some nonlinear combination of these three matrices. It is called the similarity measure. Somewhere it's called the attention mechanism. What is happening here, actually, you are trying to look for the most important part of the sentence, for the most important words in your context. And that's actually how it works. Then we have a bunch of fully connected layers, and of course, the normalization and the output, so just to make it a bit nicer. And that's a wonderful topic, but I will not cover this fully today. This should be the separate course for this stuff. What you have to understand from here is just more than 99% of all of the parameters of large language models are linear layers, are some matrices. So like W3, W2, W1, this Q, K values, fully connected layers, they all are just some linear matrices. Of course, there are some, some tensors, but they represent less than 1% of all of the parameters. So yeah, all of the parameters are just matrices. This information will be useful for us. Then we have these blocks, as I mentioned, stacked, and the output of every single block, we give it to the input of the next one. And that's exactly how large language models work. That's it. So the problem of large language models is that the combination of this block construct a model with number of parameters more than billions or even trillions. So that makes the large language model is very large. Actually, that's why large language model has this name. And this is a problem because in order to run such a model, you have to have powerful GPUs or very powerful CPUs. So you have to have very expensive machines. If you are a small business company, if you want to run a startup where you have AI assistant, you have to buy a bunch of GPUs, which costs more than $10,000. This is a problem. And what I want to achieve, I want to make the model a little bit smaller, a little bit more easy to run on smaller and cheaper devices. Yeah, this this is the introduction. If you have any questions, you can ask right now. I can give you like 1 minute to think about. This is a very simple stuff, but nevertheless, maybe some of you have some questions. You might think, what question do you have? I give you some time. One simple question, and we will continue. A linear parameter and a tensor? That's a good question. We call linear parameters, so we think that they are the same. Tensor means that actually you have like three-dimensional or four-dimensional tensor, you know? When you have just two dimensions, you have a linear layer, the matrix. You have rows and columns, but tensors can have like 3 dimensions, 4 dimensions. And that was, so I told you that in the context of this input x, because if you have just a bunch of input words, for every word you have the high dimensional representation, and then you have a matrix. So this is not a tensor actually. This is, you know, this is just one case of tensor. But if you have a bunch of sequences, one sequence, the other one, so during the training, you actually, you are trying to include several sequences at the same time. So that means that you will have additional dimension here. So this is not, in this case, the x will not be a matrix, this will be a tensor. But we are not considering this case right now, to make it simpler. Okay, any other questions? Okay, let's continue. Yeah, the most complicated part is large language model. We want to make it smaller, and all of the parameters, or much of the parameters, are just some matrices, and we multiply the input x on these matrices. We can, you know, represent the matrix in the form of just some gray dots. We are not really concentrating on their values, but you know, let's imagine that we have some matrix, and these gray dots are some values. How we can make this matrix smaller? We can, for example, try to use lower bit representation. What does it mean? For example, instead of float 32, we can use something like float 16. Why not? That is actually one of the, you know, one of the most broad, widely used scenario on how to make it smaller. You can even try to use integers. You can use int 8, but not, you know, in a way you might think, because if you just truncate all of the numbers from this layer and then leave it without floating points, you will not have great results, because, for example, all of your numbers can be in a range from 0 to 1. So what you actually have to do in order to represent the floating numbers by integers, you have to find the maximum value, the minimum value, and then define the range. And then you can define the mapping from the integers to float numbers. But that's not what I want to tell you about today. I want to tell you about the other method. We can remove some parameters completely. We can make them 0. And for example, the simplest way to make parameters 0 is just to select the smallest one. For example, red one here is one that are the smallest. Green one, they are the largest, so we leave it here because they are important. If you remove all of the red parameters, the smallest one, you will not, you know, this is a great baseline actually, and that was used for neural networks, even for large language models at the beginning, but that's not really effective. It turned out that if you remove half of the parameters, the performance will be very bad. It will be hallucinating, it will be giving some strange outputs, the perplexity will be high, everything is bad. Why? Because actually we are trying to, for some reason, when we remove the smallest parameters, we just look at the input on this weight matrix W, but in real life, we don't have only W. As I mentioned, we also have this input X. And the action of this W is the multiplication of these two matrices. So probably we have to take into account also the input X here. Because the output of the linear layer is always the multiplication of these two. And what we really want, we want to minimize the difference between, let's call it W hat, the linear layer after pruning. So imagine that we removed some of the parameters. And then W is the original matrix. The matrix where we have all of the parameters as initial. And then we take the difference between these two. This is actually the loss that we have when we apply the linear layer. So now you see that this is a very, that intuitively this makes sense. We want to minimize the difference between the output of the linear layer before and after we remove some parameters. So if it is very small, if it is 0, the output of every single linear layer will be the same. And of course, the performance will be great, and so on. Here you can see this Frobenius norm. It's just the sum of all of the elements from the matrix squared. It's the analog for L2 norm, but for a vector, for a one-dimensional vector. For matrices, we have this Frobenius norm. We want to sum all of the elements and square them. Let's denote the difference between W and W hat as delta. So yeah, of course, we can take this X from both of these matrices, take it out of the brackets, and call W hat minus W as delta. So actually, the loss is delta multiplying X. If we are not removing anything, delta will be 0, the loss is 0. That's great. So no questions for now. Any questions? Yeah, that should be simple. If you have any, just wait a bit and ask a little bit later. So we want to minimize this loss. But this loss can be, this Frobenius stuff can be written in the following way. For every single row, we can write it as a L2 loss, L2 norm. But with delta is just one row of the matrix. Yeah, this might be tricky. So actually, you have this delta multiplying X. You want the Frobenius norm. This is sum of all of the elements squared. And you can write this as L2 loss for every single row. This should be understandable. But is it? So yeah, you just decompose the full matrix into sum of the L2 norms, because every single L2 norm is just sum of the squares. So that should be understandable. Okay. So we want to minimize this loss. And now the huge matrix appeared, which tells you that we want to simplify this problem. Let's remove just one parameter from the entire matrix. Not many, because it's complicated. Let's remove one and see what we have in this loss function. So you see that this is delta I. If you have parameters for removal in the kth row, that means that only the delta k will be non-zero. All other rows will be 0, because you are not removing any parameters from here or there. So delta there will be 0. And from this sum, you will have only those that, only on the kth row. So we can rewrite this loss for this particular case when we want to remove just one parameter in the following way. Then we have this loss function. C? C is the number of rows in a final matrix. When we multiply this delta on X, we have the matrix, which is of size C times something.
What is C represent? I don't want to see what a variable means. Like, you mean the numbers of rows, yeah.
Yeah. This is, I'm sorry for that. That might be a little bit tricky, but C here is the number of rows. No, it's not. It's number of columns, but I guess in the matrix, let me see. No, it's not number of columns because you decompose this to delta, like before we have this loss function. Let me roll it back. This one, delta multiply on X. And we want to decompose this as the sum for every single row. So delta I here is a row. So that means that C is the number of rows in delta. It's not the number of columns. Yep. So we have, as I mentioned, we want to remove just one parameter at a time. It's much more, simple work to be done. So now we have this loss function where delta k is just one row. One row with this one parameter for removal. We can rewrite this in the following way. I just, replaced delta k with delta. So just to make it nicer. So in the end, we have the following loss function. Delta multiply on X, where only one parameter of delta is a one-dimensional vector for this one particular row. In this particular row, one parameter should be removed. So only one delta here is non-zero. And we want to minimize this. We want to find such a parameter in a row that will be minimizing this loss function. Because this loss function represents the difference of the output before and after pruning. And we can solve this problem right away. So we have this loss function. We can represent this delta as this vector, where WQ is this one parameter from the initial matrix. Because we know that this parameter should be removed. That means that delta here is equal to minus the WQ. So since we have this L2 norm, we can, forget about this minus. So delta for this particular case, if you remove parameter, will be just the parameter itself. You want to zero out this parameter. The delta is the parameter itself. All other deltas are zero, because only for this parameter, this parameter will be removed. And then we have this matrix X. And we multiply this delta on every single column, the first one, the second one, and so on until the very end. And what we see is that this parameter they will be multiplied on this entire row, meaning that all other x's will be multiplied on 0. That means that this parameter will be now here, and this entire row can be written in this vertical form. Doesn't really matter. So I think if you have any questions now, you can ask. This one is understandable. Like, you have delta, one parameter for removal. This is just one parameter. Then you multiply this row on every single column. You have, you have this one. And you can rewrite this in the following way. This is the final version. This parameter here, if you take it out of this L2 norm, that will be squared. And this vertical x is written like this. So that's it. This is the loss function when you want to remove just one parameter from the kth row in the qth column. And what you actually can do, this is called the pruning metric, and this is called Vanda. This is a much better version of what we described in the very beginning. When you want to remove the smallest parameter from the matrix W, that's not great. But if you remove parameters with the smallest this value, the result will be much, much better. So here you can see that we have the weights squared, and also we have some input x. And that makes sense. In order to understand what parameters are not really important, you have to take into account not only the weight itself, but also the input for this one parameter. Because the parameter might be small in absolute value, but the input might be very large. So when you multiply these two, the output might be very important for the next linear layer. So what you can do now, because you want to remove not one parameter, of course, you want to remove several parameters. But this is the NP-hard problem, to select the smallest, the best combination of parameters for removal. If you have just one, we have the solution for one parameter. And what we do, we just apply the greedy solution. We select half with the smallest pruning metric. And that's it. Then we remove all of them. And that works much, much better. But we have the solution. This solution is only optimal when you remove one parameter. This is the very important stuff. So we apply this in a greedy manner. Of course, we have some kind of optimal solution. It's not optimal in a sense, in a mathematical sense. But in order to solve an NP-hard problem, you have to apply some greedy algorithm. But also, we're trying to remove some parameters. But what if we try to tune to adjust other non-pruned parameters? So for example, here, this, and all other red are removed, but green one, they are left as they are. So we didn't change them. Maybe if we change them, the result might be much better. And that was exactly what SparseGPT did. We have this loss function as before, delta multiply on x. And then we have this constraint that the qth weight in this row should be removed. So that means that the delta is equal to minus the parameter. Now we consider this as the optimization problem. And delta, like before, on this previous example, we believe that every single delta here, every single delta is 0, but this one is not 0. And we can find this solution very easily, just multiplying these two matrices. But now we can try to tune other non-pruned parameters. So you have the same problem. You have one parameter for removal. But now, so you know that this should be delta q. But now we try to make this non-zero to make the result better. Because when you remove one parameter, you may adjust others to compensate for this removal. In order to solve this problem, it's a little bit more complicated problem. We have to write this loss function, then we subject to this constraint. This can be written in the Lagrangian form. This is the Lagrangian function for this problem. Then we take partial derivatives. We see the point when it's equal to 0 and find delta star and lambda star for which we have the smallest loss function. For this particular problem, the delta star should be the following. Delta is just this one row in which we remove one parameter. It consists of several terms here. It's not that, that easy to understand from the first view, but it's not really something complicated because H here is the Hessian matrix. It can be computed by XX transposed. X is the input, as we described before. So you just take the input X, multiply it on the transposed version of itself, and you have the Hessian. And what is great is that it doesn't depend on the row in which you remove the parameter. So for every single row, for all rows of the matrix, the Hessian will be the same. This H matrix will be the same. And this is the update rule. Let's find out how it works. For example, you have this matrix, you have this one parameter, you want to remove it. How to remove it? You apply this update rule that we obtained from this Lagrangian problem, from this solution, and then as a result, this parameter will be removed and all others will be updated. To select parameters for removal, we just take this delta and substitute this in the loss function, and we have the following stuff. It's just a Lagrangian at the optimum. It's a little bit different from what we've seen on the previous step. With Vanda, we had like the input x. Here we have h, the Hessian -1 q cubed. It's very similar to a. It's like the Hessian is very related to x. So in some sense, these two metrics are really, they are the same. What we do, we actually compute this metric for every single parameter in the matrix. Then we select the smallest for removal. And what we do, we consider the first row. Then we see that the first parameter for removal here is this one. This solution is just for one parameter. We cannot remove all at once. So we proceed step by step. And then we consider this parameter. We apply this update rule for every single parameters in this row. They are updated. Then we move to the next one, apply the update rule, but now you see the problem. The problem is that this update rule will also make this parameter different from the previous step. That means that if we zero out this parameter on the previous step, the update rule on the next step will be making this non-zero. This is a problem, and in order to resolve it, you have to change the Hessian matrix. You have to exclude these parameters from the consideration, and then you have to recompute this h-1 because now you have not b parameters, you have b-1 times b-1. This parameter should not be considered, and that's how we proceed. Then we remove it, we move to the next parameter, and then we update the Hessian again, not to consider this two that was removed on the previous step. So I think it might be a little bit complicated. If you have any questions, I can tell you what's happening. So actually, we want to remove all of the parameters, all of the red parameters from here, one by one. And we, one by one, apply this update rule. Now it's a little bit more complicated than one from the previous step, because on the previous step, we didn't tune these green parameters. We didn't tune them. Now we are trying to remove parameters and tune them on the way.
So every removal, the second iteration, we need to recalculate the Hessian matrix.
Yes, exactly.
So, and for every input x, we need to do this procedure separately, so independently, which means, but the calculation of Hessian matrix is very expensive.
Yeah, it's very expensive, by the way. That's a problem. Okay. That's a problem, yeah. Because if you have, even if you have one example, the x will be a matrix, and you have to, for every single parameter in a row, so just for you to understand what's the problem here. To remove these parameters, you should not find the inverse of the Hessian once. You should find the inverse of the Hessian for every single parameter you remove. And that is the problem. Why? You have to recompute the Hessian and the inverse of the Hessian, because when you move to the next parameter, you have to avoid consider this parameter on the previous step. You already remove it, you don't want to touch it. In order to do this, you have to recompute the Hessian and its inverse. That means that you have to, the number of operations increase drastically. And you do the same for this row, then you consider the next row, you remove parameters from here. For every single parameter, you recompute the inverse of the Hessian. You do the same for the next until the very end, and this is a very complicated procedure. This can be done, but realistically, that's not going to happen. What is really happening, In SparseGPT, they consider the entire column. As I mentioned before, the Hessian matrix is the same for every single row. So the Hessian is XX transposed. It doesn't depend on row. What they do, they consider the first column, then they look for parameters for removal in this particular column. So this green should not be removed. We just skip it. We see that this is the red one. We have to remove it. We apply the update rule for this row, update all of the parameters, effectively removing this one parameter, move to the next row. We should not prune it, we skip it. Now we have to remove this parameter. We apply the update rule. All of the parameters from this row will be updated. And we do this until the very end of this particular column. We update all of the parameters that should be removed. And the good stuff here is that we don't have to recompute the Hessian, since on the first iteration, we have to consider all of the parameters. So we compute the Hessian, that's it. Then we move to the next block, and what we do actually, we forget about these parameters. So we are not considering them anymore. As you can see, that parameters for update, we remove it by 1. We compute the inverse of the Hessian in this case, but this again can be reused for every single row in a matrix. So now Hessian is recomputed, but it's the same for every single row, and we can proceed with the same iteration. We move to the parameter that should be updated, and then you see that we update only those parameters that comes after this brackets, after this caret. So we are not considering parameters from before, purely to avoid the complicated Hessian computation for every single parameter in this matrix, just to make it simpler. Then we move to the next parameter. We update all of the parameters from this row, excluding the previous. So in this case, we see that this green parameter should not be updated. Of course, if we are able to compute the Hessian for every single parameter very effectively without a cost, we would compute the Hessian for every single parameter and update this one, but we don't have such a luxury. So we have to be careful. That's why we consider only parameters for removal in the front of the sequence. We skip the last 2 parameters, move the caret further, and then we see that parameters to update is decreased. Then we recompute the Hessian again, do the same stuff, and remove all of the parameters from this particular column. And then we apply this update rule every single time, but you see that parameters for update is decreasing, so we are not considering this part of the sequence. And that helps us to avoid the complicated stuff with matrix, like matrix inversion, Hessian computation, because we have to compute the Hessian just for the entire column, and that will be the same. And we avoid this complicated part. It turned out that it works well. We update every single column, step by step. And then, of course, the number of parameters for update will be smaller and smaller until the very end. So that's how we apply this update rule and remove parameters. So actually, nothing really special or complicated here. We just apply the same as we did before with Vanda. We computed some metric for all of the parameters in a greedy manner, but instead of just removing them, we applied some update rule, and that helps us to make the result a little bit nicer. But of course, it adds some complexity to this process, because now we have to tune these parameters. And the other problem is that also we select these parameters for removal in the very beginning. But now, as we can see, we update parameters column by column, and parameters on the right part of the sequence can be changed drastically. So after a while, we can have the matrix with important parameters that are not the same as before. So probably we don't have to compute the full matrix from the very beginning. We have to compute the beginning of like the full several parameters. For these parameters, we pre-compute the mask of parameters that should be removed. Then we consider the same procedure, like in this block. We remove parameters column by column. So that's how we prune the entire block. Then we move to the next block, and only then we compute parameters that should be removed. So that's in this manner we allow parameters for removal to be updated, because the matrix can change dramatically now. That's exactly how SparseGPT works. But yeah, as I mentioned, even with this, modifications, with this stuff that we consider all of the columns, we do not consider this part of the sequence. Even in this scenario, it's much, much slower than Vanda. Vanda was the first one when we didn't tune other parameters. But it's slightly better. That's how we did SparseGPT. And now we have several questions. What if we prune several parameters at a time? Because before, in all other cases, we try to remove several parameters at a time. We try to remove just one parameter. Now, I suggest you to consider several parameters, and the update rule was just for one parameter. And also, this with local pruning mask, as I mentioned, we are not computing the full mask of parameters for removal. We just compute it locally in order to, compute this after we update these parameters. But because we do this, in SparseGPT, we force every single block to have a fixed level of sparsity. And when we have this constraint that every single block should be 0.5% sparse, so it might be, the result might be slightly worse. Yeah, if you have any questions, as for now, you can ask. Let me scroll it back. Yeah, in general, I think the algorithm should be understandable. We want to tune parameters, not only remove them. And we do this in a column-wise manner to make everything simpler. What I suggested to do in my work, now we come to the part where my contribution is, what if we consider several parameters at a time? Let's move to this part. We have the same objective function, the same delta multiplied on x, but now instead of one constraint, instead of one parameter, we have a bunch of parameters. That's it. That's the only change. You see, previously we have, with SparseGPT, we had like one parameter. Now we have S parameters for removal. That's it, nothing special. And this is the just illustration of what's going on, because before we had one parameter, now we have S parameters, and we want to remove these parameters. Q1, Q2, Q3, and so on. It's the indices of parameters for removal. In this particular case, it's 2, 4, and so on. Yeah, and you have these constraints. This problem can be solved by writing the Lagrangian as before, and we will have the following update rule. This is the optimal delta that should be to, remove several parameters at a time and tune all other parameters. This is the update rule. It's a little bit complicated. Let's censor it for now. And consider how does it work in essential. We just take this update rule and add to, this update rule removes every single parameter that should be removed. We have S of these parameters. And also, this update rule updates all of the other parameters that should not be pruned. This is good because before, when we remove parameters one by one, we considered only those that comes after. Now, when we want to remove the entire row with all of the parameters at once, we can apply this one update rule, and that will remove every single parameter in a row and update all others. So this is the optimal solution when you remove several parameters in a row, not just one. That's how it's constructed. This is the update rule. The matrix R here is just some combination of the hashing. It's a very simple process. This is the hashing matrix, and then we take the Qs1 row, the Qs2 row, until Qs, and that's how we construct the matrix R. It's so easy. You can write this in Python, like in several NumPy code, lines of code. The same with R hat. It's constructed from R, nothing special, and U is just parameters that you want to remove. So U actually is the vector of those parameters for removal. You just stack them, that's it. That's the update rule, but here the difficulty comes to play because you have to invert this R hat if the number of parameters S is really large. You have to do S cubed operations, which is complicated. And that's why we do something similar to SparseGPT. We consider not all of the parameters in the block. We consider just several, a block of parameters. And then now we move like our caret by 4 elements at the same time. We can see that in this particular case, we want to remove just one parameter. The solution will be exactly the same as before, because before was a solution for when we want to remove just one parameter. And then, of course, you update all of the others. The same on the next row. You update these two parameters optimally, and also you update all of the parameters in this row. And that's what you do. You move to the next one, and remove parameters, in this particular case, by a block of 4 parameters at a time. Then you move this block onto the next one, select parameters for removal, do exactly the same, and now look at that. We remove 2 parameters, and we update only parameters that comes after the current block. In the same manner as we did in SparseGPT, we are not considering this part to make this computation much more simpler than it was. And that's actually how it works. This is the update rule. If you want to remove several parameters, not just one, you want to use my update rule. The second contribution was with the pruning matrix, with the pruning mask, because here we force every single block to have the same level of sparsity, but that might not be the best solution. So I tried to elaborate this. I tried to think what we can do. And the solution was the following. We compute the mask for every single parameters, as is the very beginning. But then we select only parameters from this part and forget about these parameters. So now this block doesn't have the fixed level of sparsity. And we do this for every single block. We recompute parameters and then select parameters for removal and continue. So nothing really special. It's a little bit change over here. The change in that now instead of just considering this single block, I consider all of the parameters that should be removed in future and select only those parts that is interesting for us at this moment. Yeah, it might be a little bit tricky, but if you have any questions, you can ask. Yep.
What is the efficiency and the processing power that is gained by this migration?
Can you repeat, please?
When it comes to computing power,
Yes.
what efficiency do we gain typically from this?
It comes to compute power.
The computing power.
How much power do we save by using?
How much more efficient becomes?
You mean when we how much we save when we are not computing the hashing for every single parameter, comparison to what if we don't consider
The whole data without any reduction.
So if you consider just if you do not consider this part and try to compute the hashing only on the parameters that now are in the sequence that should be removed, you compute the inverse of the hashing only once for all of these columns, for all of these rows, I'm sorry. If you want to remove, if you want to consider this part also, you have to do this computation for every single row. So that means that it will be, if you have C rows, it will be C times more expensive. So instead of one computation of the inverse of the hashing, you will have C computations of the inverse. And now, in order to, like, I will give you some numbers. In order to prune the model by SparseGPT, you have to wait something like maybe 10 minutes, 10 or 15, something like that. But the metrics here might be something like 4,000 by 4,000, so C is equal to 4,000. So you multiply 10 minutes on 4,000, and you have like 50,000 minutes, something like that. So it is like, it might be, the reduction is just in C, but you know, if C is very large, that comes to play. Even this is very important. Yeah, when we are talking about large language models, just for your understanding, the size of this linear layer is something like from 4,000 until something like 12,000 elements. Yeah, and as I mentioned, I did some slight modifications of how we select parameters for removal, because actually the problem of selecting the best parameters for removal and updating them is very complicated. And what we do actually, we split these two problems. We firstly select the parameters for removal, and then we update other parameters that should not be pruned. So ideally, of course, we would have some algorithm that solves these two problems at the same time. But that's much more complicated. Okay, yeah. I guess, yeah, I have more slides, but because I don't have more time, I will finish here. If you have any other questions, let's spend this 5 minutes on your questions. Or if you want to repeat something, you are welcome.
So yeah, so if not, I have two questions.
Okay.
So the first question here is, it seems all the pruning method is a question to the general field of the model pruning. So all the pruning methods, they are based on X, which is the input.
Yeah, in some sense, yeah. Like recent works, they are all, it's called data-aware pruning. Yeah, they all based on X.
The input will change for every.
Yeah, that's true.
Really works?
So actually, the way we did this, thank you for your questions. That's a wonderful question, by the way, because that's a very important question. Like, if we want to prune parameters for removal, we compute this which parameters should be removed by this X over there. But how we select X from what we have it? In our case, we used C4 data set, and we evaluated perplexity. For those who are not aware of what perplexity is the measure how the model is sure about what will be the next token in the sequence. And if the model is not, like, is hallucinating, is not quite sure about what is going on, the perplexity will be huge. We evaluated the quality, the perplexity on Wikitext2, and we selected this X from C4 dataset. And that was like 128 samples from C4. But of course, like, if you want your model to work best for mathematics, that might be a good stuff to take this X from mathematical dataset. If you wanted to be good at something else, you might use another calibration samples X. Yeah.
I see. So even for the cipher-10 data set, so every image is X, right? Or so for every image, every input, you will have different model parameters.
Yeah, but what we actually do, yeah, that's also a good question. X here is just one image, let's say, or a bunch of words. So that means that for different images or for different words, this pruning metric will be different. And what we do actually, we compute this for several images. And then we measure the average value of this metric for all of this.
So yeah, I have a second question is, I think your slides is gorgeous. If you don't mind, do you want to explain to the audience how to make a fancy, good slide like this? How to do that?
Yeah, if you are interested how to make these slides with animations, you can use, like, all of the stuff that I used is just some PowerPoint functions. So it's a regular PowerPoint presentation, and you may use a very important trick. I found this trick on TikTok. Let's say you have two slides, and let's insert something like a box over here, and then you have the same box on the next slide. For example, the box will be like this. Let me center it. Now, if you slideshow this, of course you will have something like this. But this is not beautiful, isn't it? It's, and that's what's happening in most cases when you do some presentation. But then, look at that.
Oh, you can choose the transition.
Yeah, you go to transitions here, you select these two slides, and apply this morph.
Oh, yeah.
This is very important, guys.
Yeah, sure.
I found this on TikTok, and when I found it, like, oh my gosh, I didn't use it.
Okay.
Then you press, and look at that. Let's slideshow it again. You have this. Ooh, ooh. And this works for every single vectorized graphics, because this one is vectorized. Of course, if you have JPEG, that will not work like that. But if you work vectorized objects in PowerPoint, that will work just beautifully. And that's how most of the presentation was done.
Okay.
Thank you.
Thank you for sharing. I think this is the most important part of this presentation. Thank you for sharing the
Yeah,
trick
that was
of
just a demonstration of what I will be teaching
Thank you for teaching us how to make our slides fancier. And thanks for the talk. I hope you all more or less learned something. And I also hope everyone is happy with the calling today. Thank you.
Thank you very much, guys.